Now, when we talk about rational expressions, we're really talking about a polynomial in the numerator, a polynomial in the denominator, and seeing if we can simplify them by canceling out polynomials, all right? Remember, when anything is over itself, we can reduce it down to ones, right? Well, that includes polynomials. So let's look at example 7. We have x plus 7 and over 7 plus x. They don't look the same, but if I were to change them around and write the variable first, I would see that they are exactly the same. I kept the signs with them. Now, we can't usually reduce when there's addition in terms, but in this case, we can consider this as a binomial in the numerator and an identical binomial in the denominator. I'm putting them in parentheses to show that I'm treating it as a single term, okay? I can cancel those out. They both become ones, and 1 over 1 is just reduces down to the number 1. Let's try another one. Example number 2. In the numerator, all I have is a 2. In the denominator, I think I can factor that so that I can factor out a number, okay? So here I'm going to factor this out so I got the greatest common factor coming out of it. I'm going to say 8 will go into both of those. And I'll factor it to 8 plus 2. Now, after I've factored out the greatest common factor, I'm treating this binomial x plus 2 just as a single term that's being multiplied times 8. So it is multiplication that I'm considering, and I can reduce the 2 and the 8. The 2 would go into both of those. I have in my numerator, all that's left is a 1. In my denominator, I have 4 times x plus 2. And that's the way I would leave it. I would not distribute that multiplication again. And I do need the 1 in the numerator because there's nothing else there. So remember, when something reduces down, it leaves a 1, not a 0. And I need the 1 if it is just in the numerator, if it's the only thing there. Let's look at example 3 and see if we can factor out some greatest common factors. 7x plus 35. I can factor a 7 out. What's left is x plus 5. X squared plus 5x. I can factor out x. What's left? X plus 5. And now I have matching binomials that are multiplied times other terms. Remember, I can only reduce when I have multiplication. I'm only able to reduce these addition signs or these operations that are addition because they're inside a binomial that's being multiplied times something else, right? So I can reduce those, and this reduces down to 7 over x. Now let's take a look at number 4. This one looks like I'm not going to be able to reduce it at all until I remember my factoring. So this looks like a complex trinomial up here. Let's see, how do I factor that? 2 binomials. The signs all have to match the first sign because the second one was positive. I factor the x squared. I set my factor statement. My statement says add to equal 11. And I have to factor a, which is 5, and I have to factor c, which is 2. 1 times 5, 1 times 2, and I'll reverse those, 2 times 1. Now I'm looking for something, combination that will add to equal 11. I'm not going to try everything. I'm just going to kind of look at these, and I think it's going to be this one. 5 times 2 would give me 10. 1 times 1 would give me 1. Those add to equal 11. I'm using those numbers, 1 and 5. And 2 and 1. FOIL it to check. X times x is 5. X times 5x is 5x squared. 2 times 1 is 2. 2 times 5x is 10x. And x times 1 is 1x. That gives me 11x squared. I've checked it really quick. I know it's over this binomial, x plus 2, which I'm going to put in parentheses so that I can show I'm treating it as a single term. Now, I can reduce matching binomials, right? These match. In the denominator, I still have a 1 because it reduces down to a 1, but I really don't need ones that are left in the denominator. They just make the term a whole number. So it's really 5x plus 1. As we go ahead simplifying rational expressions, we'll find that any kind of factorization problem might be included. So what you have to do is look at your numerator and look at your denominator and see what you need to do to factor them. In example 5, I know I'm going to be factoring two trinomials, the numerator and the denominator. I'm going to go ahead and set the signs of both of them. In the numerator, it's plus plus. In the denominator, it's also plus plus. I'm going to factor my x squares. And then I'm going to create a factor statement for the numerator. It is add to equal a 7. I'll have to factor a, which is 3, and c, which is 2. That's 1 times 3, 1 times 2, and I'll also reverse the factors of c. Now I'm looking for products inside and outside that will add to equal 7. I'm getting pretty good at this, so I see the combination I want. 3 times 2 is 6, 1 times 1 is 1. Those add to equal 7. So I factored the first one. I'll just plug these in, 1 and 3, and 2 and 1, and I would do a quick FOIL to check. Now let's factor the denominator. The statement is going to be, this time, add to equal 13. A is equal to 3. It has to be factored. And c is equal to 4. It also has to be factored. I have 1 times 3 is the only ones there. 1 times 4, 2 times 2, and I'll reverse those. 4 times 1. Inside and outside products are what I have to compare. Draw the arrows if you still need that. And then I'll say, add to equal 13. Well, when I look at 3 times 2 is 6, and 2 times 1, this one doesn't work, does it? But look, I think I can see the combination that's going to work for me. 3 times 4 would be 12. 1 times 1 is 1. That would add to equal 13. So I'll use 1 and 3 in the first positions, and 4 and 1 in the second positions. Remember, I'm not writing 1 when it's a coefficient of the x term, because we need to get used to not doing that. So it's really 1x, it's just written as x. Now, what's matching that I can reduce? Well, 3x plus 1 in both of them. So what does this simplify to? X plus 2 over x plus 4. Now at this point, sometimes we look at it and we say, why don't the x's reduce? Because they are identical. Look carefully. They are added to those other terms, and we cannot reduce unless what we're reducing is only involved in multiplication. The only reason we're able to reduce binomials is because they're being multiplied times something else, and we're reducing matching binomials. All right, example number 6. In the numerator, this is factoring by grouping. Remember grouping? When you have 4 terms, you group the first 2 and you group the second 2. And if the sign in the middle is positive, then it's easy. We don't have to worry about factoring out the negative. Let's go ahead and factor those. I factor out the greatest common factor in the first binomial I've created. It's x times x plus y. And I factor out the GCF in the second one. It's going to be plus 2 times x plus y. I'm just going to put down x plus 2 down here in my denominator because there's nothing I can do to factor that. Now, let's finish the grouping. I pull out x plus y as my first factor pair, my first binomial, and my second binomial is whatever is left over, and it's x plus 2. Let's go ahead and fill in the denominator, which was x plus 2, and see that I have x plus 2's that match. I can reduce those. They both become 1s, remember? So I've got x plus y in the numerator, 1 in the denominator, and 1 in the denominator does not have to be written. So my answer is x plus y. Now take a look at example 7. This looks like, the numerator looks like 2 perfect cubes, and I know how to factor a sum of 2 cubes. I set it up as a binomial times a trinomial. I set the signs, matching, opposite, positive. I take the cube root of the first term and the cube root of the second term. And then I use the binomial to say, square the first term in my binomial, x squared. And I say, square the second term, 2 times 2 is 4. Multiply the 2 together, 2 times x is 2x. What do I have down here in the denominator? I still have x plus 2, which I can't do anything with. I'll just put it in parentheses to show that I'm using it as a single term. They cancel, and the solution, what's left, is x squared minus 2x plus 4 over 1. And remember, 1 is the denominator, I don't have to write. Now, let's fix number 8 so that we're actually factoring it the way it should be. We're going to move the terms around. Negative y squared plus 49. But I don't like that much. I'll go ahead and write y minus 7. Because I can't start factoring when I have a negative term first. I'll factor out the negative, which causes me to switch the signs of both terms. Still in the denominator, it's just y minus 7, which nothing I can do with it. I'll just keep it, hope it matches something that I can reduce with later. Now, how do I factor a difference of two squares? Well, I have two binomials, opposite signs, square root of the first, square root of the second. And in the denominator, y minus 7. What does this reduce to? Well, these y minus 7s will go away. I'll have negative y plus 7. Better probably if we distribute this negative. Negative y minus 7. Either correct, either one of these would really be accurate as a solution.